Okay.
Good evening. We like to start on time so we can leave on time. Thank you very much for attending this science-based information program. We're really appreciative of Dr. Avner Vengosh for contributing his time. He's probably about 9:30 somewhere there in North Carolina, and he's had a very busy day. And so we really appreciate the fact that he's taking his time to share with us his knowledge. I'd like to welcome everybody here in Dawson City, Mayo, and other communities that are listening in. We really tried hard to connect with all the communities. My name is Don Roberts, and I, along with over 8,000 Yukoners, want to ban fracking and LNG in the Yukon. Yukoners concerned have been working for 5 years to educate ourselves and Yukoners on the negative aspects of fracking. This evening, Dr. Vengosh will be discussing the environmental risks for shale gas development, radioactivity, and fracking, lessons from the US, so we can learn from the US. Whitehorse has over 260 tons of drill waste from Eagle Plains that is stored in the Arctic backhoe site in the quarry on Mount McIntyre. This drill waste was never tested for radioactivity. We are not here this evening to discuss regulations, mitigation. That will not solve the whole objective of the negatives of fracking. We have made our mind up that fracking is not good. It's not good for the Yukon, and it's not good for the world. Fracking destroys the water and many other environmental components forever, and that would be tragic for the Yukon and Canada, despite what people say that there's a lot of positives. YTG's geological survey by Petrel Robinson, we're hired by Petrel Robinson from Calgary. It's a geological firm, and completed a study in 2012 on unconventional drilling, and they stated that the major geological areas for drilling, like Eagle Plains, the Liard, the Cotinili, and many other areas, are mainly shale structure, and the only way to extract these fossil fuels would be to frack. And this is in their report that was submitted to the government in 2012. Now, Dr. Avner Vengosh is a person who has been to the Yukon once before. We met with him about 1.5 years ago, and we discussed some issues around the whole area of fracking. And he has recently just completed a major report on shale gas and what is happening to the environmental risks of using it. Dr. Vengosh is a professor of geochemistry and water quality, a division of Earth and Ocean Sciences at the Nicholas School of the Environment. He's from Duke University, North Carolina, and he will, in a couple minutes, be presenting what his findings are. We'll have a Q&A after the presentation. Even the communities will entertain questions from there. They can call the contact number that we've given them if they want to ask a question of Dr. Vengosh. The other part of it is that we have a little program out here because we're preparing for the next election. We have 30 days, 30 facts. If you have received one of these, maybe while you're listening, you might want to put down a fact that we could use in the 30 days and just drop it in the basket that's out there in the hallway. We basically want to make sure that Yukoners are considering what is going to happen in the next couple months. We also have a donation jar out there. This is something that we, as a I guess you would, an NGO that with no basic funding, all it's by contribution. If you want to throw in some money there to help us out, we are paying for this tonight. We just believe it's very important that we do this. And in 2 weeks' time, we're going to have Dr. Ingrafia from Cornell. He'll be doing the same thing. He'll be giving us a talk on the negative aspects of the whole issue of fracking. And he is the godfather of fracking in North America and actually the world. Much of the stuff that they're using in fracking today are due to what he and his colleagues have put forth. And when he found out what it was doing to the water, he became a foe. So I would ask questions. Again, the number that I've already presented to the rural areas. If you have a question, we're not going to take any questions during the presentation. But as to set the pace here, I'm asking my good colleague here, Angela Sobo, who's going to set the pace and sort of give the opening as to what we are going to be dealing with here tonight. Dr. Vengosh, welcome. We thank you. And right after she finishes her speech or her talk, you'll launch into yours. Thank you very much.
Hello everybody, and thanks for the introduction, Dawn. Thank you all to be here and join us. And I want to give a short introduction to tell you why we're concerned. This picture here is taken from page 12 of an attachment submitted to the designated office in Dawson City on August 27th, 2015. It is part of Northern Cross multi-well drilling proposal south of Eagle Plains, where the company holds leases for over 40,000 square kilometers. Okay, so what we're seeing here, and it's taken out of a technical report on the management of natural occurring radioactive material. The abbreviation for that is NORM. That's what you see there on top, and it is approved from Professor Vengosh that it contains the right information. So we see a typical setup here for drilling. This could be conventional or unconventional. For unconventional or hydraulic fracturing, you have to add another pipe here in the shale about 2 kilometers long. And you would inject a fracking fluid to that. In both cases, you have to extract drill cuttings out of either just vertical or vertical and horizontal. And we're concerned about whether or not these drill cuttings could be potentially radioactive, because in the shale layer here, we're finding uranium and thorium and the decay products. And in the attachment, it tells us that we're part of the Western Canadian sedimentary basin, and we have significant uranium deposits in this area. So our shale layers do contain heavy elements. This is uranium and thorium here. These elements are very heavy, so they usually stay in the reservoir, and they're unstable, so they decay or produce offsprings. In this case, radium-228 and radium-226. And radium-226 again emits radon gas here for all of its lifetime. So the reason that we're concerned about the drill cutting is because we're not sure whether they will be tested and where they would be stored. The second thing is, between these two shale layers, we see what it's called formation water. The formation water is deep under us in the earth and has been there for a long time. It is very saline and also carries radioactive products. Radium-226 and radium-228 and radon gas are very light. They're volatile, they're reactive, and they're water soluble. So what happens when we initiate the drilling procedure is they're going to come up with a so-called produced water and make it to the surface. Some of them will react here and get deposited as a scale. They will react with salts or sulfates. Other ones who make it to the surface could be deposited in the wellhead, in the pipes, in any type of storage containers or trucks. And they're still radioactive at this point in time. You see here radon gas is still emitted. And our second and third concern is where will the produced water be stored? Will it be safe? Will it be radioactive? Will it be re-injected, or what is the solution for that? And the third concern is the people who are working with this equipment here, and they have to clean trucks and storage container. Are they going to be protected by WCB? And I'm honored to pass the presentation on to Professor Vengosh now. Thank you very much.
Can you see me? Hear me?
Yes.
Right. Good evening, everyone. Thank you for having me tonight. My name is Avner Vengosh. I am professor of geochemistry, and I will talk to you about our work on research on fracking in the US. I will talk a little bit, present you about fracking, talking about the water footprint, talk about different types of contamination associated with fracking, what we call stray gas contamination, then the issues of fluids contamination and radioactivity that has been mentioned right now, and how we actually identified fracking fluids in the environment. Fracking in the US, as you know, is a big thing. It took over many of the energy development in the United States, and already almost getting 50% of the natural gas production in the United States, and the same with oil. Unconventional oil is becoming a major source of oil in the United States and projected, if things continue to be into the future. And the basins of oil and gas in the United States and Canada, you can see in this map, are distributed. You can see the different colors for oil and the different color from gas. In the United States today, basically the distinction between conventional and unconventional is becoming very small. In most cases, they're almost everywhere using fracking for extracting oil and gas in different basins. And also you should be aware that this is going globally. Many countries like China, Argentina are starting to extract unconventional oil and gas, Australia as well. And there is a huge potential all over the world. And what are you facing in Yukon is some question that many people around the world are asking themselves. So this is kind of a global issue. So first, let me give you some introduction of hydraulic fracturing. This is a well, a rig that we took a sample in Pennsylvania. And the landscape is going to be changed, is going to be a lot of those kind of pictures if indeed fracking will take place in Yukon. The idea of fracking that you having a vertical well that turn into horizontal within the shale formation, and then you take water and chemicals and basically inject with a high pressure into the formation, which generate fracks and structure within very low permeability shale, and that's fractured, opening space within the shale and causing hydrocarbon, oil and gas to be extracted from the shale. This is kind of another way. Basically, you see that the blue reflecting injection of water into the shale, and the water, this is the fracking fluid, is generating fractures, and then the water that is, and the gas that is recovered, you see is together with formation water and the return flow water, and they're both returning to the surface, what we call flowback water, together with the gas or the oil. So this is basically the principle of generating flowback water and produced water from the fracking. And over time, as I'm going to show you, this becoming produced water and the gas and oil that are being extracted from the shale gas. One of the things that make shale gas and oil unique is that only the production is valid only to the first 6 months. And after about 6 months, the amount of gas and oil is decreasing dramatically, and orders of magnitude in many cases. And this is a time series for different oil and gas. And in order to keep the production economic, they have to drill many, many wells. So this is something that makes fracking, and people not aware of that, the intensity of drilling is something that associated with fracking. This is a map of in Pennsylvania, and probably it's not updated. We see 7,000 shale gas well only in Pennsylvania from being installed the last decade. And basically it's changing landscape. As you can see, in North Dakota, we're also talking about thousands of wells. You see the little dots in the Bakken Basin, which also share in Canada. You can see it's thousands of wells, and that's something very important. This is the way it's going to look like, the landscape. These are pictures below, the picture from North Dakota. This is an aerial photo. Because of the need of the drilling many wells, this is going, you see high intensity of well. For each square kilometer, you can see a dozen of well installed. And that's going to change the landscape. And it has been, as the example in North Dakota. There are several environmental risks associated with shale gas and drilling. There's issues of how much water is used. There's issues of fugitive emission of methane to the atmosphere. And methane is a gas that causes global warming. There's issues of methane contamination of drinking water wells and the water becoming on fire. There's issues of contamination from the fracking chemical or fracking itself. There's issues of air pollution and the health implication and quality of life. There are issues of disposal of the wastewater, which I see one of the major issues in a place like the Yukon, what to do with the wastewater that is generated. So there are many issues. I'm going to focus on only a few of them, but it's important that understanding that there are many associated issues that could be coming with fracking. And one of the main issues is traffic, noise, and having kind of industrial zone rather than the natural environment that you have right now in Yukon. And that's something that is going to accompany it, even if we have no contamination whatsoever, but there is going to be a major change in landscape, major change on way of life once it's taking place. And as you know, there's a huge public debate fracking around the world. There is evidence for water being on fire. There's this Gazland movie that made a lot of noise and awareness. There are many communities around the world in the United States. New York State, for example, there's a ban on fracking. It's true from other states, and also other countries like France and other European countries are banning fracking. There is a debate between the industry and environmental groups, as you know. And one of the problems in the United States that the fracking is exempt for the federal environmental regulation, and therefore there's no much environmental evaluation, unfortunately, and regulation of fracking in the United States. And each state have its own evaluation and own addressing it in different ways, so it's making pretty chaotic situation in the United States. And as you know, there being a lot of protest and kind of environmental movement of fracking that you are very well aware. In our research team at Duke, we're working on different aspects of what is called the energy-water nexus. We're working on coal mining, coal ash disposal. We're working in not far away from you on the impact of tar sand. And we also work on shale gas and fracking, and we're all trying to understand the differential impact on the environment of those different technologies. And the talk of today, I've shown you kind of a collaboration from different organizations in the United States, and also the French Geological, BGM, the French Geological Survey, Yale, Stanford, the University of Rochester, and Ohio State University. And we've been working in Pennsylvania, West Virginia, Texas, Arkansas, North Carolina as a baseline. We're working now in California and Colorado and in the back end in North Dakota. So we collected thousands of wells, thousands of water samples all over the state to understand the different issues that are associated with fracking and shale gas development. And one of the papers we published is a review paper that gives an overview of the environmental impact. And if someone is interested, I'll be happy to provide this paper that gives all the detailed information published in Environmental Science and Technology in 2014. In the nutshell, we see, when we talk about water, we see three major issues. One is the water footprint, how much water is used, and this can be affecting areas when water is scarce. Groundwater contamination, which associate with what we call stray gas contamination, when the water can be saturated with methane. And the third component is surface water contamination, could be spill, leaks, and inadequate disposal of the wastewater that in many cases resulted in accumulation of toxic residue, including radioactive elements that was mentioned by Angela, that are being accumulated in areas where it's being impacted. And I'm going to show you this later. And in this graph, we're trying to synthesize the different pathways of water contamination. Water contamination, you can see in the arrow, can be from leaking from the well in different parts of the well. It can be part for gas flowing through fracture in the system. It could be taking place in the surface when ponds and holding storage are leaking and into the groundwater and to the surface water. The treatment itself, they tried to do it in Pennsylvania. It wasn't much successful, and we see contamination of river. And even when they dispose it to the deep aquifers, the question is where the water is going, the wastewater, and that could also affect drinking water aquifers. So understanding the different pathways is pretty complex, as you can see. It could be multiple contamination ways. And in our research, we're trying to understand the different pathways and a different mechanism of contamination. So first, I'll talk a little bit about the water footprint of hydraulic fracturing, how much water is used, and whether water scarcity can limit fracturing, and some arid zone in the world can be affected. We published a paper last year talking about the water footprint of fracking, and we provide a very basic information how much water per well is used, the average, the median values, and the range in the different major shale gas plays and the major tight oil basins in the United States. They're pretty similar. We see large variation through this. This is based on thousands of well, data from thousands of well. And we can see that we see variation in the water use in either million liters or thousands of cubic meters around the different places. And the map that you can see, it's water scarcity in many areas in the western United States. There is a severe water scarcity that could limit, or fracking could compete other water sources. We tried to quantify that throughout the United States, and we found that overall the water use is small if we talk about from a nationwide. But if we look in the small companies, small areas, the watershed, the impact could be pretty much in small areas. The second part I want to talk is about the stray gas contamination. This is a picture that you can see on the right, that you can actually, in cases when the water is contaminated, you can put the water on fire, and this fire would be burning of the saturated methane in the water, and you just lit it up, and it could be all night looking at your well or your water faucet coming on fire because there's enough methane to provide this source of gas. And this is a problem because that poses a potential inflammatory explosion hazard to homes and home near shale gas site. It's causing in many sites in Pennsylvania shutdown of the private wells, and they need for looking for alternative source. And it caused some real damage, as you see in the left, where the well exploded and people got hurt and burned in some areas. This is a case in Texas. And there's some issues of methane oxidation and causing sulfate reduction, which is another human health problem from formation of a gas, secondary gas, H2S, into drinking water well. And there is a very strong debate right now in the United States. Some scholars, some of them supported by the industry, say everything is natural occurring. There's no any contamination, whereas we suggested, based on our data, that there is a high risk in some wells, subset of wells that are located near shale gas well. And we have several studies. This is the first study we published in 2011. It published in the Proceeding of National Academy of Science, where we showed that then there's another study. In those studies, we showed that wells located less than a kilometer from the nearest gas well have high concentration of methane relative to wells that are located far away from the shale gas well. We also showed that those wells located less than a kilometer from a shale gas well have different chemistry that associate with gas that comes from natural gas from wells and different from the gas that will be natural occurring. And we also use isotopic fingerprint to show that the gas that coming from wells located less than a kilometers is different isotopic fingerprint relative to gas that occurs in wells away from the shale gas well, in drinking water wells. So we have kind of compelling evidence, and then we published in 2014 another study that we use noble gas geochemistry to further demonstrate that the gas that affecting drinking water well coming from actually directly from the shale gas. And we use this cartoon to explain that we can actually identify gas that coming naturally occurring through flowing into the aquifer relative to gas that being leaked from the shale gas well. So we have a kind of a very compelling evidence to show the impact from shale gas well that happening, causing gas contamination. And this is something that led to debate, as I mentioned, but we saw evidence in Pennsylvania and Texas that indeed there is stray gas contamination from shale gas wells. The third part that I would like to talk is about water contamination from hydraulic fracturing fluid, and that's mostly the wastewater, and that's what I like to give more time because I think that's very relevant to Yukon, if hopefully for your sake not, but that's the major risk of contamination. I'm going to show you that there will be uncontrolled spill. There's a huge high frequency of spill in areas of high drilling intensity. There is potential contamination of surface water and shallow aquifer from spills and leaks in storage reservoir. Disposal of the wastewater without really adequate treatment is really dangerous for contamination of rivers and waterways. And then I'll talk about the accumulation of radioactive elements in stream and soil that going to having a radioactive legacy over time. And then there are some other issues like potential formation of carcinogenic disinfection byproduct in downstream drinking water rivers, and I would show you this as well. So one of the things we found that the water that injected into the well, as I show you in the beginning, the water that coming back is composed of a mixture of the formation water and the return flow. This is the water that we injected in, and they're both coming to the surface. And we can see that the volume of the water during the first 6 months is high and goes down. In most cases, after 6 months, the volume goes down. But the salinity of the water is going up really fast in the first couple of days. And basically, we showed that the water in the flow back is composed of increasing contribution of the brine, the natural occurring brine that is coming from the shale formation. And when we look over time, this is data from the USGS, we see that the salinity stabilizes after couple of months, it's becoming stable over time. And in a study that is going to be published in a couple of, I think next week or so, and we're showing that most of the water that's coming back from fracking is composed of this formation water that's entrapped within the shale formation. And there is a high volume, you can see the high volume of the water during the first 6 months after hydraulic fracturing, and the level is much lower after a year, 2 years of production from those shale gas well. But still, we're talking about relatively high salinity. And we see the salinity is pretty high in different parts of the country, and the same high salinity was observed in the basin in Canada. So what's in flowback and produced water that we need to worry about? First, there are inorganic contaminants. We found that there are high level of ammonium. Ammonium can kill any living things in water, fish, and biological life. Barium, strontium, and selenium, and other metals that are extremely toxic to the environment. Then there are issues of salt, halides, chloride, bromide, and iodide that is problematic, and I'll explain to you later. Then there's naturally occurring the radioactive material that Angela mentioned, and most people are concerned of man-made chemical, but they are actually pretty small, and the natural occurring contaminants are as effective and more persistent over time. And that's the major difference between the salt and the inorganic contaminants. They are not going away like organic contaminants that can be degraded over time. And I'll show you that later. So this combination would cause differential impact on contamination. And I would like to show you that, I will show you in a minute, that having natural occurring radioactive material causing long-term accumulation of those radioactive elements in sediments or in soil. So in spite of, if you take away the spill water, you already contaminated the soil or sediments of the river, and that is going to happen for the next thousands of years without ability to, even if you took away the water. So this kind of contamination is irreversible with respect to the radioactivity because it's affecting the solid, not the water. In the United States, they try to do a different way of management of the wastewater. They try to treat it. It's a problem. They try, in the United States, 80% of the wastewater is being injected into deep injection well. However, we see result of induced seismicity, meaning earthquake. So probably you've heard in the news that recently there have been several large earthquakes in Oklahoma and Texas. They are all because of the deep well injection of the wastewater. And the wastewater is a major issue. If you are release it to the environment, you would cause a major contamination. If you inject it into deep injection well, you could induce earthquake. And we see this evidence taking place in Texas and Oklahoma. In some places in New York, believe it or not, they're spreading the fracking fluid and produced water on roads as part of the de-icing. This is the last thing I would recommend you to do in Yukon. In Pennsylvania, there were several sites that actually have an attempt to treat the brine that's coming and dispose it in different places. And even today, in some places in Pennsylvania, the outfall, this is a Franklin site that we see contamination of the Allegheny River, and the water salinity that goes into the river is 10 times the salinity of seawater. So imagine a brine going into a pristine river, causing a major contamination. That's, again, you don't want to see that. Don't do it at home. You don't want that at the Yukon. And we see high contamination of bromide in the water that is being affected by this disposal. And we see also in the river, this is a cartoon that showing the level of the radioactivity in the sediments and accumulation of radium in the sediment that is much higher from the level of radiation threshold. This is level of radiation that you need a licensed radioactive waste disposal facility. And we see that the level that actually we measure in the sediments of a river from downstream from the disposal site exceeding this level. So in fact, you have to take this water and solid and to put it into certified radioactive disposal site, which I believe the closest location is 2,000 kilometers away from Yukon. So this is a serious problem, what to do with the wastewater that's coming from hydraulic fracturing. I mentioned the bromide, there's high iodide, very high ammonium. A typical ammonium, 1 milligram per liter can start to have impact on aquatic system and causing fish kill. We found hundreds, and in the Bakken we found 2,000 milligram per liter of ammonium. This is a real potential impact in addition to the radioactivity. Here's the level of the high radioactive level in the different brines in the United States. We see that they have a typical different ratios of isotopes that enable us to being able to identify the brine and tell whether it's coming from unconventional versus conventional source of oil and gas wastewater. And one of the things we found that one of the danger when you have even simple salt like bromide and iodine being disposed to the river, when you take, if living downstream from the river and you take the water and try to use treatment like chlorination, you could actually generate, because of the high bromide, disinfection byproduct. Disinfection byproduct are man-made chemicals that are generated if you are chlorinate fresh water with organic matter, and if it has tiny addition of bromide, you're actually causing your own contamination of the drinking water. So this is a real problem that we see in areas where they dispose the wastewater. But the most common thing that's going to happen is spills. And spills is something that is inevitable from fracking. It's happening all the time. In Pennsylvania, we found that the higher numbers of wells per square kilometers, this is the red zone that you see here, is associated with much higher numbers of water spills associated with fracking. In North Dakota, we investigated the spill very extensively. Here you can see that the numbers of wells is unbelievable in North Dakota. And we worked on that to try to understand what's in the spill. So in those green points, we actually collected water to analyze it. And this is the brine spill that took place in North Dakota between 2006 to 2014. We're talking about over 4,000 brine spills that took place all over North Dakota. And here's another zoom into that. You can see the magnitude of the brine spill in gallon, from some small, some very high. And we see that the brine spill, again, associated with a high intensity of the well. Remember in the beginning, I told you that in order to get unconventional oil and gas, you need to have high intensity of drilling. And this high intensity of the drilling result in higher frequency of brine and oil spill. And that's something that is happening in North Dakota, mostly from leaking and bursting of pipes. Currently, the pipes are not adequate design to hold the brine, which is highly corrosive, and in very harsh condition of North Dakota and Yukon, they cannot holding and they are leaking into the environment. And we see strong correlation between the oil production in time to the number of the brine spilled in time. It's going hand by hand. The more oil production, the more wells, the more spills. It's like 1-to-1 ratio. And we studied it extensively in North Dakota, and we published a few months ago a study. And this is one of the sites that we investigated. This is called the Beer Den spill. It took place in July 2014. And the yellow arrow here, this is where the spill took place, where the pipes were leaking a huge volume of oil-filled brine. The brine moved downstream, and you can see all these areas. This was taken in the summer. It's pretty green and lush there, and you can see that there is the pathway of the spill through the ecosystem cause actually a dead zone of no vegetation and no anything growing anymore in this area. This is where we actually collected sample. This is the spill that took place a year later. And so the water is still there. And you can see around the spill that all vegetation is dead. We find high level of salt, ammonium, vanadium, boron, and natural occurring contaminants. And the interesting thing, we found not only in place where we found the water, but we find the radioactivity legacy also in the soil, in areas where we don't see any of the brine anymore. But the brine, the radioactive elements from the brine being attached into the soil and left behind. So the radioactivity zone is still there, in spite that actually the brine, the water itself, is moved downstream to this point. The fourth point that I would like to mention that we use different chemistry and different isotopes to understand and evaluate fracking. So in our tools, we are capable to go to a site and using kind of a detective work, forensic tracer, that tell us if the contamination is because of shale gas, because of coal mining, because of coal ash, or many other source of contamination. So we are able to do that using the different isotopic ratios. And here is an example because we can see the difference between the isotopic fingerprint of conventional oil and gas versus unconventional oil and gas. So we have a very strong tool we have developed that provide us with the ability to identify fracking fluid in the environment. And as I mentioned, we're using radium isotopes also as a tool for being able to do this distinction. So, in conclusion, there are many issues associated with fracking. A lot of attention has been given to man-made chemical, but natural occurring contaminants are as effective, dangerous, and they include salt, ammonium, trace element, metals, and natural occurring radioactivity. The stray gas contamination is real, and we have strong evidence for that. And finally, wastewater is one of the major challenges associated with unconventional oil and gas. And if it cannot be disposed through deep injection well, this is a major risk to the environment. And even injection through the well now causing earthquake in some areas in the United States. So for me, this is the most kind of the highest risk. And without a really detailed plan what to do with the oil and gas wastewater and how you monitor it and how you store it and how you treat it, without doing that, you're going to have contamination of water resource. This is kind of seems like inevitable and need to be addressed and need to be very careful about that. So I think I will stop here. Thank you for your attention.
Thank you. Excuse me. And thank you very much, Dr. Vengosh. I think you've put it in very succinct terms. I think it's made it very clear that the hazards that will go with any kind of fracking wherever. And I think you've done a great job. We much appreciate your science. I think the important part is that this has to be shared amongst people so they understand what's going to happen to them. And that's just the beginning, because as you know, we have other issues here with permafrost. We have issues with the huge, probably the biggest porcupine caribou herd in the world that exists up in that area. And so there's a lot of other issues that we could throw on the table as well. And to go down this path, rather than stay where we're going in the sense of using our environment as a natural environment for the world to see, I think is the real challenge. And I think your comments are much appreciated. We're going to have some questions now, but we want to stick to the issue here. We're not going to go down the path of looking at, as I said earlier, with regulations and mitigation. We're not there. Our group has said very clearly, we are not going to move down the path of approving or saying that we can regulate this into a positive movement. We will only have to go over the border to BC and see what's happened around Fort Nelson. All you have to do is talk to the First Nations in Fort Nelson, and they tell you very clearly they can't hunt anymore, mainly because the animals are all drinking the fracked water. They have to take water with them. So there's a lot of major issues. We don't have to go too far. We don't even have to go to North Dakota. We just have to look over what's happening in that area. And we have to remember that this is a boom-bust type of business. Just ask Albertans. I come from Alberta. I have a lot of my relatives that are no longer working in that area, and they don't think it'll ever come back. Anyway, we'll leave it at that. Questions? Anybody have questions for Dr. Vengosh? Over there, Luke, I think.
Well, hi, my name is Luke. I have a question. You can go more in detail about radiation because it's so broad, and which level they're allowed to dispose to everybody out there. So any database about radiation? Thank you.
So yes, so the radiation depends of exposure, depends on many factors. But the point that Angela has pointed out, and I try to demonstrate in my talk, is that the water that's coming together with oil and gas, they expected to have, in some cases, elevated level of radioactivity. And the question is how this water is being transferred and what's happened to that. If the water is being discharged to the soil, the radioactive element in the soil will be attached to the soil and start to generate radiation, which the risk is being bioaccumulate in the ecological system. And when you have that, you could have accumulation of this radioactive element in first in the soil, in the grass, and the animals that eat the grass, and then eventually in human who eat the animal. So that's one of the risks of the radiation. And again, the risk depends on how those radioactive waste water being treated, being addressed, being managed, and that's kind of the risk that's associated with that.
Hi, my name's Shane. I'm curious what the economic benefit of this is. Like, how much does one of these things actually make? Because I don't understand how anyone with a brain can think this is a good idea. It's got to be purely based on money, and I want to know how much money. Do you have any of those statistics?
No, I'm not an economist, and I guess different economists will give you different numbers. One thing I can tell, our data clearly show that you need to drill a lot in order to get the production. And that's what we've seen in so many places, because after about 6 months, the volume of gas or oil that's being generated goes about orders of magnitude lower than what you had during the first 6 months. And then over 5-10 years, you have kind of a tail of production. How economic it is, I cannot tell you. Probably the companies, they would know. Probably it depends also the prices of oil and gas. There are many factors into that. I'm not the person to tell. But the one thing I can tell is that usually when you're doing economic evaluation, you look at the profit at hand, but you don't see the big picture. And the big picture would be what's happened to the infrastructure, to the roads, what's happened to the human health, which is cost money, as we know, what happened to environmental remediation 50 years later. And one of the risks I have seen in many places is the boom and the bust. So the first years at the time of the boom, there is prosperity. But then when its resource is gone, is depleted, then the energy companies leave the place. And this is the bust of how to build a community that is not dependent on the energy. And that's a major challenge to many communities around the countries that have to deal with the day after and whether they have enough resources at the day of the boom to keep for the rainy days later on. But again, that's not my field.
Thank you.
Hi, I just wanted to ask about, I think you called it re-injection of wastewater into the ground. It sounded like that's a solution that industry is proposing, and you seem to leave the door open to it. It just doesn't make a lot of sense to me, and I don't understand it.
So the point here, I mean, if you think about it, it could be the best solution because releasing this water to the environment is problematic. Another solution is treatment, but that costs money. So that would energy company trying to minimize that. Now, if you have injection, depends your injection to where. So in many cases, the injection takes place into a deep aquifers, disconnected from the freshwater aquifer. In most cases, they're supposed to be salty aquifers, so you're not actually contaminating freshwater resources. If those conditions take place, that could be a possibility. However, in California, for example, we have just recently discovered that produced water from oil and gas, conventional oil and gas, being injected into drinking water aquifers, and oops, realized that they did some silly mistake in contaminating potential freshwater resources. So this can be done, but there are many issues that could be associated with that. And the latest issue, as I mentioned, would be what we call induced seismicity or earthquakes that are being generated because of the injection of the wastewater.
Just a scientific question here. There's what you've got up on the graph on the screen right now. What do you attribute the difference in isotopic ratios between conventional waters and unconventional?
It's interesting. I actually argued that there is no much difference. The difference depends where you're talking about. I mean, if you are drilling in the Bakken, conventional and unconventional, you will have very similar wastewater chemistry. Only the first month or the first 2 weeks of production, you will see different chemistry from this chemical that's coming from the fracking chemical, but everybody is so aware of them. But during the lifetime of a well, the chemistry of the wastewater will be naturally occurring brine. But this naturally occurring brine, in some cases, could be more toxic and more effective negatively effective to the environment. I'll give you an example. In North Dakota, our study found that the brine, because it's composed of naturally occurring inorganic chemistry, they are resistant to biodegradation. So if you take oil and release it to the environment, there is, of course, a huge impact immediately, but the oil is being biodegraded over time. So 10 years later, the oil will be degraded to basic compound, and you see kind of release of the impact. Whereas if you have radioactive elements or ammonium or other inorganics, they are not decay. I mean, there is a radioactive decay with radiation, but they're not going away. They're resistant to biological biodegradation. And that's make them actually more dangerous and risk over a long time.
Thank you.
I'm wondering how frequent and widespread the freshwater aquifer contamination is in a deep well injection scenario.
Well, there were only a few cases in California that were suggested that some of the operation injected those produced water into wells that actually penetrate into aquifers that could be used also for domestic consumption. I don't know how many, but there's some investigation right now in California about that. But that's kind of a risk that should be avoided, of course, in any coast.
Thank you.
Thank you. Hi. You mentioned that earthquakes in Texas and Oklahoma were being caused by fracking. Is that associated with the number of wells or with the volume of water that's being re-injected?
So the earthquake, at least in Texas and Oklahoma, is not associated with the fracking itself. It's associated with the wastewater that's being injected into deep injection well, designed specifically for that. The problem is that if you have a large volume of water that's coming, because, again, the large volume of water is because of the intensity of the fracking and of the intensity of the drilling. And as a result, you have a large volume of water, this large volume of water causing what we call liquidation of geological fault. And in this process, you would trigger an earthquake along a fault that is existing underlying the injection well.
Thank you. Just a short question there.
Two short questions.
Well, one to start with.
Good presentation from the angle of geochemistry. First question, why did you leave the perfing gun out? 1, drilling, 2, perfing explosives, 3, fracking. Industry presentations often leave the, otherwise there wouldn't be fracking possible, right? Without holes in the casing. Anyways, secondly, you summarize the outcomes always with the word risk, even though some are risk and some are certain harms. And that's also another sort of bias that favors industry. That's, you know, in summary, that's often used by industry public relations to describe even certain harms as risk. Why do you summarize certain risk harms also as risk?
Thanks, Peter.
So can you? It was not clear the two questions. Can someone with a mic can repeat it?
Question number 1, why did you leave out the perfing gun? That's often done by industry to sort of beautify the process, leave the perfing explosives out of the description. Number 1. Secondly, why do you summarize the outcomes as risk when some of them are certainly risk, but others are certain harms? And you summarize it all as risk. That sort of introduces a bit of a bias. in favor of oil and gas. You know, I mean, this is not a detailed critique. Your presentation was very enjoyable and seemed all very, very well founded. I'm just questioning, why do you summarize all the harms as risk?
I'm not sure I understand the question. I'm sorry.
Okay, I think what he wants to know is that you use the word harms rather than risks. And why do you say, oh, the other way around, sorry. Some of them are, from his point of view, more risks than they are harms. There's a okay, whatever.
Well, I'm not a lawyer, so if you are want to be a kind of...
We won't hear you. Can't hear you. No, I think it's good. I think the question is between risk and harms.
So in areas like North Dakota, it has been harmed. We see, I mean, there was a picture, very clear picture that in that area, the spill caused harm. So there's no question about the ecological harm in those areas. We are using the term risk when we're talking about general potential effect in other places. Of course, in the Yukon, it's only a risk because nothing happened. But in North Dakota, in this case that we are showing here, it's not a risk, it's actually harm. So we are very careful with what we are saying, and actually we're showing only in cases that we see evidence. When we see either spill or we see contamination of groundwater, we only saying it's effective when we have a very strong scientific evidence that indeed it's happening. So in those cases, it's harm, but when the way we present it is potential risk from other cases.
It hasn't happened yet, that's what you're saying. Yeah.
In some cases it's not, in some cases it has.
It has. Okay. It has. The other thing was the perforating process, using a perforating gun in some of the injections. You didn't talk about the perforating process that they use as well.
I'm not. My knowledge about that is very low, so I'm not part of the industry operation, so I cannot comment on that.
Okay, we have a few questions from the communities that have come in. So the first one, well, they're both actually from Dawson City. And the first one is, why is wastewater disposal so difficult in the Yukon? I'm not sure if you can speak to the Yukon context, but if you can, that's the first question.
So, again, I know that you guys don't want to see it this way, and I apologize in advance that I'm saying, but in a case that you do have that, you need to build the infrastructure to how to manage it. So I'm saying the Yukon is more complicated and more difficult because first you don't have the infrastructure, you don't have the history that many basins in the U.S. had, and the most important thing, the extreme temperature condition in the Yukon. That's what we've seen in North Dakota. I think many of the spills associated with the harsh condition of the north. And the pipes just not designed to hold 10 times seawater salinity and not to being leaked into the system. And that's why the major challenge in a place like the Yukon, how to make sure that the wastewater is being handled correctly without leaking out to the environment.
Okay, and the second question, I believe, is with regards to this slide about the bear den spill. Why was contamination higher further away from the spill, if that's the interpretation of the visual?
Well, it's a great question. It's related to the chemistry of the water. So at close to this kind of yellow, to the arrow here, the water was highly saline. This is the brine water. As they move down, they're becoming more diluted because they're mixed with other water. And we have demonstrated and shown that the more diluted the water, the more radioactive element will be retained and absorbed into the soil. So basically, the more dilution you have, the more radium will be attached into the soil, and therefore we see higher concentration downstream relative to the upstream.
Couple over here. I think we'll take 2 more questions, and then I think we'll close.
I have one more technical question to the radioactivity. The last slide you had up with the intensity of radioactivity. Can you explain the danger to the biosphere compared to the numbers in Becquerel? As far as I know, the norm that's not really dangerous, any radiation is dangerous, but a level of 0.5, and I seen in your slide there, in your graph, it went up to over 200. So
okay. You referred to the spill. Okay, yeah.
Yeah.
Well, I mean, you should take those numbers. I mean, in everywhere it could be different. Here is an example in Pennsylvania. The number were over almost 5,000 or more. So it depends where, and it depends on the intensity. Every site will be different. But the principal issue is that not to take to the absolute numbers, but rather that once you have soil with radioactive element, like any other contaminants, there is always the risk of bioaccumulation. Bioaccumulation meaning that those metals will incorporate into the ecological chain from the soil into the grass, and the grass into the animals that eat the grass, and this kind of bioaccumulation would result in even higher concentration in the biological system. We haven't measured that yet in any of the data, but that's the risk that exists from studies, and other studies have shown that in different metals.
Last question.
Thank you very much for your presentation. Have you or your colleagues been able to establish a correlationship between the amount of contaminated water caused by fracking, and can you give an American, United States figure as to how much water actually exists? So is there a correlationship between, in other words, what is the amount of contaminated water? What is the amount of fresh water that exists in the United States?
Well, we did this study. We in the earlier phase, we tried to evaluate what would be the overall impact of fracking, using water for fracking, from different basins, and we have some values for the water use, and we have some sporadic data on contamination. I don't think we are seeing a large-scale impact. The impact is very domestic. It's very local. Even in North Dakota, this huge spills, the impact is only in the immediate environment. It's not spreading to overall water resources. So we don't see a risk for water resources in the United States because of fracking. But I think for someone who's been working on water resources, I think it's important to see the domestic. That's the key for having water availability. So if you are a community in Texas and you are struggling with water availability, having water contaminated or used for fracking can be a big deal, although in nationwide or even for Texas state, it's not a big deal. But for the local person, it could be a big deal. I hope that's answered the question.
Well, thank you. We have just one more quick question here.
Yes, hello, Dr. Vengosh. I'm wondering, what do you think about the EPA who proposed last June? EPA's protective action guide that would allow the general population of United States to drink water 100 to thousands of times more radioactive than is now legal. For example, a radioactive iodine 131 has a current limit of 3 picocurie per liter in water, but the new guidance would allow 10,350 picocurie, 3,450 times higher. For strontium-90 high-cause leukemia, the current limit is 8 pCl. The new proposed value, 7,400. So this is kind of the EPA, United States, that is willing to allow more radioactivity in the water. So I'm wondering, what is your idea about this, please?
So yes, we measure those levels. So in the figure that I showed earlier, these are the numbers, in fact, that's what we show. We show that in different, here you can see in picocurie values, so some of them, as you mentioned, in the Marcellus, they could be up to 6,000, 7,000 picocurie per liter. There's in the Bakken is a little bit up to 2,000. This is in produced water, and indeed the drinking water regulation is 5 picocurie. So indeed we see huge radiation relative to the drinking water standard. But I hope you can see that in the slide here. So again, here's the up to 6,000, in the Bakken is 2,000, and drinking water standard will be very, very here. But the point is that if indeed this water is injected into drinking water well, you cannot drink this water. That will cause massive contamination and directly human health. And that's why we are saying that it's impossible to let this water to be injected or disposed into clean water source and fresh water that people would drink the water. That's why I said that the wastewater has the highest risk potential because of the spill and because of the potential release of this high radioactivity to the environment. Now, even if you don't drink the water, my argument that you can have biological bioaccumulation and have a long-term effect in the ecosystem in addition to the risk to human health. But yes, you don't want, the bottom line is, this is the water you don't want to drink.
Well, thank you very much. I'd like to take this opportunity, Dr. Vengosh, for giving us an excellent presentation, very science-based. I would just like to remind people that on the table out there, there's a card that's on climate change. It was in sort of response to the fact that there was supposed to be a forum here by the MP to discuss climate change. That hasn't happened yet. Larry hasn't got that together. But there's a card out on the table out there that you can sign off and say, look, we need to have that discussion. That's all related to what we're doing today. As well, just a reminder that on the 29th, Dr. Ingrafia will be here again to do a presentation on his work. And he's, as I said, the godfather of fracking in many issues in more ways than one. If you haven't heard him, you can Google him very easily, and you can find that, you'll see a lot of information on him. And don't forget our donation jar. Yes? This presentation will be on YouTube, I gather. That's my understanding, Jason? Yes, it'll be on YouTube. So thank you very much, everybody, for showing up. This is great. I know it's a long night, but Dr. Vengosh, you did an excellent job. Thank you.
Thank you.